Hey guys, I wanted to just put together a quick little video on empirical formulas and just do some calculations with you guys. Just do a couple of empirical formula examples so that you get a better idea for how these work. So if you guys don't mind, I'm going to just do a couple problems. And hopefully this provides you with a little bit of a little more guidance, a little more help. So I'm going to do one of each of the type of problems. So let's start with one where you're given the amounts of the elements. So let's say that we have a compound that contains nitrogen and oxygen, and it's decomposed in the lab, and it yields 1.78 grams of nitrogen, and it yields 4.05 grams of oxygen. Now we're going to calculate the empirical formula. Now I've got a periodic table in front of me, so I know how to get to moles. 1 mole of N is 14,00674 on my periodic table, and 1 mole of O is 15,9994. So I'm going to plug these into my calculator. I don't have these numbers pre-calculated, so you're going to have to bear with me while I... This gives you a chance to follow along too, though. So this is 0.127 let's say 1 moles of N and 4.05. This is 0.2531 moles of O. Okay, so we've got our moles of each. Now the next step that we do is that we divide it by the smallest number. In this case, it looks like the 0.127 is the smallest. Now this has the effect of always giving us 1 mole of something that we can compare to other moles. So always the smallest number divided by itself gives you a 1. 0.2531 over 0.1277 is 1.98. Now 1.98, that's close enough to 2. So let's say that there are 2 moles of O for every 1 mole of N. Since we are at whole numbers, essentially whole numbers, 1.98 is close enough that we can call it a whole number. Then we have our formula. Our formula here is N1O2. So the first empirical formula we calculated was NO2. Let's do another one. Let's say that you are given not the masses, not the decomposition masses. Let's say that you're given something more like, let me try to find, here we go. You've got 1.45 grams of phosphorus. Now phosphorus burns in the air. We're going to assume that that forms a compound with oxygen to form a phosphorus oxide. So it's some kind of metal oxide, or phosphorus oxide. Phosphorus is a non-metal, so a non-metal oxide. We've got 1.45 grams of phosphorus, and we form 2.57 grams of the oxide. Okay, so we know our mass of the phosphorus. Grams of phosphorus, 1.45. Periodic table says that 1 mole of phosphorus is 30.973761 grams. Now, how much oxygen do we have? Well, the total weight, remember, conservation of mass, has to be the masses of the reactants. So 2.57 minus 1.45 reveals that there is 1.12 grams of oxygen. And since we already know the molar mass of that, we can do our calculations. So 1.12 divided by 15,9994. And for our 1.45 grams of phosphorus, it is 0.0468. Smallest number here is the 0.468. This is going to give us a 1 for the phosphorus. 0.07000 divided by 0.0468 is 1.495. 1.495. Let's call that 1.5. It's close enough to 1.5 that we can make that rounding. So this says that there is 1 phosphorus to every 1.5 oxygens. Here's where we have to multiply now to get rid of these decimals. What can we multiply something that's 0.5 by to get a whole number? 2. So 1 times 2 is 2 phosphoruses, and 1.5 times 2 is 3 oxygens. So we ended up with P2O3 as the empirical formula for this problem. This one we were given gram amounts of a product and a reactant, not decomposition amounts like we did in the previous problem. Let's do one more of these. Let's say that this time we're given percentages. So let's talk about methyl butyrate. That's apple flavoring. Methyl butyrate is composed of 58.8% carbon, 9.87% hydrogen, and 31.33% oxygen. Our job is to find out what the empirical formula of this might be. So right off the bat, I'm going to say I have 100 grams of stuff. That makes all of these percentages grams. So with 100 grams of stuff, I just have 100 grams of my elements now. So carbon, hydrogen, oxygen. So we have to figure out how many moles of each we have. 58.8 grams divided by 12.011 grams is about 4.89 moles of carbon. We've got 9.87 grams divided by 1.0079 is about 9.79 moles of hydrogen. And 31.33 divided by 15.9994 is 1.9, let's say 1.96 moles. Now, the more rounding you do, the more your numbers won't be close to whole numbers. So I'm not writing down everything right here, but I would keep it all stored as a number in my calculator to make the math much easier. So let's divide all of these by 1.96. That'll give oxygen the ratio of 1 to whatever these guys come out to. So 4.89 divided by 1.96 is 2.49. Let's call it 2.5 carbon. These aren't really moles, but molar ratios. Every 2.5 moles of carbon to every 1 mole of oxygen. And then 9.79 divided by 1.96 is 4.99. That comes out, let's just call that 5. All right, so we've got a problem, right? We don't have a whole number for carbon. So let's multiply everything by 2. Everything by 2. And that will give us 5 moles of carbon to every 10 moles of hydrogen to every 2 moles of oxygen. So now we can write our formula. C5, H10, O2. Methyl butyrate. Methyl butyrate. 2, 3, 4. It's methyl butyrate if you are into organic chemistry or interested in structures at all. Okay. Let's do now a molecular formula problem, because these were all empirical formula problems. So let's look at a molecular formula problem. They are much easier. Okay. let's say that a compound containing carbon and hydrogen has the molecular formula equal to 56.11 grams per mole, and that I just calculated an empirical formula of CH2. So that's my empirical formula. CH2. All right, to get the molecular formula, we need the empirical formula. We need N, and we just multiply EF by N. Now, to get N is the molar mass of the molecular formula divided by the molar mass of the empirical formula. In this case, the molar mass of the molecular formula was given. Usually has to be. So what's the empirical formula's molar mass? Well, we just add that together. 12.011, here, let me do it this way. 1.0079 times 2 plus 12.011. It's roughly 14 let's say 0268 grams per mole. We don't need to be exact here because N is going to be a whole number and not a fraction number. So 56.11 divided by 14.0268 should get us very close to a whole number. In fact, this is 4.00019. So it's 4. N is 4. And so the molecular formula in this case would be C4H8. Let's do another one. We've got a compound containing phosphorus and oxygen. The molecular formula is equal to 219.9 grams per mole. Our empirical formula we deduced to be P2O3. Let's find N. N is going to be 219.9 divided by whatever the empirical formula's molar mass is. We need 2 phosphoruses, 3 oxygens. A phosphorus is, again, 30.973, and let's say an oxygen is 15.999. So I'm going to do 30.973 times 2 plus 15.999 times 3. Altogether, that comes out to be 109.9. Maybe I shouldn't have rounded so much. Let's see, 219 divided by 109 is 2. 219.9 divided by 109.9 is still 2. Even with my cutting short my masses on the ends here. We get a whole number of 2. So the empirical formula, P2O3, gives us P4O6. That's how we convert an empirical formula into a molecular formula. All right, guys. So I just wanted to do a couple of those empirical formula type problems for you guys. Hopefully this was helpful. See you in the next video.